Over the past few decades, humans have built many types of telescopes for space observation. Among the latest developments, the United States has just launched the James Webb Infrared Telescope in 2021. And China has built a 500-meter single-aperture radio telescope in 2016. These two are the top telescopes, up to date. In theory, both telescopes can pick up signals from 13.7 billion light-years away, a distance close to the origin of the universe estimated so far. However, these two telescopes are quite different in a lot of aspects, so let's do a comparison. These are the full names of the two telescopes. The Webb telescope is named after James E. Webb, who served as NASA administrator from 1961 to 1968 and played a major role in the Apollo program. China's FAST telescope is also called Tianyan, in Chinese, meaning sky eye. Regarding the weight and size, FAST telescope is a behemoth. Its size is about 40 times that of Webb's. And FAST's weight is estimated to be about 2,000 times that of Webb's. China's FAST telescope is built in a natural basin in Guizhou Province, southwest China, while James Webb telescope is launched into space, and deployed around Lagrange point L2, an orbit about 1.5 million miles away. Both Webb and FAST telescopes are built for space observation and cosmos research with overlapping scientific goals, but Webb and FAST are quite different in terms of working mechanisms, research targets, and costs of manufacture and maintenance. Before we get into this question, let's see why human makes so many different telescopes in general. Human eye is a set of detectors that can detect electromagnetic waves, but only within a certain wavelength range. Optical telescopes, such as the famous Hubble Space Telescope, still detect a wavelength range of electromagnetic waves similar to the human eye, namely the visible light, despite seeing farther than our naked eye. In the cosmic space, there are many kinds of electromagnetic waves that the human eye cannot perceive, including radio waves, infrared rays, X-rays, ultraviolet rays, gamma rays, far infrared rays, and so on. Although invisible to the naked eye and optical telescopes, they exist, they are real. But these light or electromagnetic waves can be seen with the help of instruments. This picture shows the entire sky of the Milky Way observed at different wavelengths. From the longest radio waves at the top to the shortest gamma rays at the bottom. The same Milky Way, but looks different when viewing with wavelength observation instruments. The entire sky in a IDOF projection, aligned so that the galactic plane runs horizontally across the center. The galactic center is toward the center of each. The conclusion is, the telescopes used are different, the wavelengths measured are different, and the pictures seen are also different, reflecting that the composition and propagation of the electromagnetic waves from the observation targets are different. Similarly, this spiral galaxy has different visual pictures at different wavelength observations. If we make a composite image from all these pictures, we were able to obtain the structure, temperature and chemical composition of this spiral galaxy. When we observe the universe from the perspective of different wavelengths, the phenomena they observe are also very different, which helps us obtain comprehensive information about the universe. Therefore, astronomers have developed various telescopes to observe the universe. Almost all of the telescopes are actually for observations of various bands of the electromagnetic spectrum. So, why is Webb telescope deployed into outer space and FAST telescope built on Earth? This is mainly because the atmosphere above the Earth has different blocking effects on electromagnetic waves of different wavelengths. Furthermore, while it would be ideal to deploy all telescopes far away from Earth, in order to avoid the effects of the Earth's environment and noise waves, this is technically not currently possible when telescopes are too large or heavy. This figure shows the relationship between the ability of different electromagnetic radiation to penetrate the atmosphere and the wavelength. The horizontal axis is the wavelength of electromagnetic waves, and the vertical axis is the absorption rate of electromagnetic radiation by the atmosphere. The yellow part shows the percentage of electromagnetic waves blocked by the atmosphere, with gamma rays and other shortwave rays on the far left almost 100% blocked. The Webb telescope detection wavelength range is partially blocked, while the FAST telescope detection wavelength range has little effect. In addition, with Earth's daily deteriorating environment of infrared rays, launching Webb telescope into space is the best option. And building FAST telescope on Earth is the only choice. The Webb telescope is an optical telescope, used primarily to observe the infrared for the purpose of seeing, for imaging, and for spectroscopy analysis. Infrared imaging does not require visible light and can be photographed even when covered with a black cloth or at night. Differently, the China's FAST is a radio telescope that is mainly used to receive radio waves for the purpose of hearing, cannot be directly imaged. The FAST receiver processes and converts these radio signals into a form that can be recorded and displayed, and performs some processing according to specific requirements and then displays it. Simply put, the working mechanisms of Webb and FAST telescopes are a bit like between TV and radio, one is watching and the other is listening. Hubble Space Telescope have revolutionized astronomical research and advanced our understanding of the universe and ourselves. Yet Webb Infrared Telescope is a much more powerful space telescope, with technology about 100 times more powerful than Hubble. Equipped with a variety of advanced detection instruments, high-sensitivity infrared sensors and spectrometers. It is foreseeable that Webb will bring more amazing pictures of the universe and develop new astronomical concepts. Any objects, including cosmic objects, with a temperature above absolute zero radiate infrared light. The light from distant galaxies is different from what we see. The emitted light have traveled a long distance before it reaches our eyes, a process that is known to cause the wavelength to become longer, the so-called redshift. So an infrared telescope is very useful to observe the distant early universe. Actually, some of the current primary infrared telescopes have already brought amazing data. But that's not to say that FAST is inferior to Webb, or that Webb is better or more useful than FAST. The working mechanism of China's FAST is similar to that of the former Arecibo radio telescope in the United States, but China's FAST is now the only radio telescope with the largest aperture and ultra-high sensitivity in the world. Although radio telescopes cannot directly image, they can still allow humans to appreciate the beauty of the universe. Cosmic dust exists widely, as well as black holes and dark energy. It is absolutely impossible for ordinary optical and infrared telescopes to see the entire universe, so the role of radio telescopes will be equally important. There are abundant radio sources in the universe, and the radio waves emitted by them cannot be observed by Hubble or Webb telescopes, which requires special radio telescopes. The supersensitivity of the radio telescope makes it have great potential in the research of radio transient sources in the cosmos. Recently, scientists have made significant progress in using FAST to measure the interstellar magnetic field in neutral hydrogen spectral lines. One paper was selected as the cover of the January issue of Nature magazine in 2022. Using the neutral hydrogen narrow-line self-absorption method, the detection of the Zeeman effect was realized, and the magnetic field strength of the L1544 molecular cloud 400 light-years away was successfully measured. It will help solve the problem of magnetic flux during star formation. The scientific community originally thought that the closer the molecular cloud is to the inner magnetic force, the stronger the magnetic force, but FAST's observations show that the magnetic force does not increase with the density of the molecular cloud, which means that there is no magnetic force during the formation of the stars. Actually, radio telescopes have made many important contributions in the past. Since Arecibo was built in 1963, in the 57 years, Arecibo has created many world firsts and is known as the glory and dream of the United States. In fact, Arecibo and other radio telescopes together have made 4 very important discoveries in 20th century astronomy: pulsars, quasars, cosmic microwave background radiation, and interstellar organic molecules. Arecibo also housed several transmitters, making it one of only 2 instruments in the world capable of radar astronomy. However, due to sharp drops in the financial budget and delayed maintenance, the Arecibo platform collapsed overnight on December 1, 2020, which has become a historical regret. In order to avoid the cost and engineering difficulty of large diameter radio telescope constructions, multiple smaller radio telescopes, like arrays of telescopes, can be combined, aiming to achieve the accuracy of large diameter telescopes by using radio signal interferometry technique. The array radio telescopes currently in operation by astronomers include the Very Large Array, VLA, and the Atacama Large Millimeter, Submillimeter Array, ALAM. In a few years, the Square Kilometer Array, SKA, will be the most powerful array of radio telescopes, maybe. Resolution is an important indicator of the quality of the astronomical telescopes. The resolution refers to the minimum distance between 2 points that the telescope can clearly distinguish. The smaller the value, the stronger the ability to distinguish, and the clearer you can see. The angular resolution of a telescope is inversely proportional to the diameter of the telescope's primary mirror, and proportional to the working wavelength. The smaller the angular resolution, the better. Since the wavelength of radio waves is much larger than the wavelength of visible light and infrared, the resolving power of the China's FAST is much lower than that of the Webb telescope. The Webb telescope's resolution is at least 500 times better than that of China's FAST. However, everything has a price tag, as we know that the accuracy of the mirror surface polishing is generally related to the working wavelength. Compared with optical telescopes, it is much easier to make the mirrors of radio telescopes, and the diameter of radio telescope is also easy to make larger. That's another reason Webb manufacturing cost is higher than FAST. Because astronomical radio sources such as planets, stars, nebulae and galaxies are very far away, when reached to Earth, the radio waves become very weak, so radio telescopes often need extremely sensitive receiving equipment. As we know, the more sensitive, the more noises from surrounding environment the equipment will also pick up at the same time. So it's critical for radio telescopes to avoid electromagnetic interference from radio, television, radar, motor vehicles and other man-made electronic devices. From the perspective of appearance, whether it is China's FAST or other radio telescopes, they all look like a complete cauldron, or half of a pot. Electromagnetic interference pollution is a factor that needs to be considered in the construction of radio telescopes. The sensitivity of FAST is very high, and it is very susceptible to electromagnetic interference. Therefore, the local government of Guizhou, where China's FAST is located, has established a quiet zone within a 30-kilometer radius, strictly forbidden to use electronic products that generate electromagnetic radiation. The airspace within the 30-kilometer radius of the FAST site is designated as the Flight Control Area. The core area within a radius of 5 kilometers is strictly prohibited to install and use radio stations, strictly forbidden to build facilities that generate radiated electromagnetic waves. It bans carrying mobile phones, digital cameras, tablet computers, walkie-talkies, drones and other radio transmitting equipment or electronic products that generate electromagnetic radiation. The maximum penalty has been raised from 5,000 to 20,000 China dollar recently. Before the construction of FAST, 9,110 residents within the 5-kilometer radius of the telescope were also relocated. The relocation costs even outweighed the cost of building the telescope itself, according to China's newspapers. Relatively speaking, although there are many technical difficulties in sending telescopes into space, especially like the ones of James Webb Telescope, the noise contaminations from the atmosphere and the ground can be avoided, so that more accurate data can be obtained. The development cost of Webb Telescope is 50 times that of FAST telescope, making it the most expensive space telescope in human history. This may reflect differences in technology and positioning. China's FAST is built on the Earth's surface, while Webb needs to be placed in space orbit 1.5 million miles away. More importantly, Webb's lift-off process also needs to go through a process of folding and unfolding. It might seem easy, but this fold to unfold is the first time humans have done it. Amazingly, Webb made it. Since Webb is so far from Earth, the Webb telescope is too far away to be repaired by astronauts. If something goes wrong with the telescope after launch, it's game over. But the optimism is that once Webb is deployed in orbit and working, maintenance costs will be very low. In fact, Webb has already done the hardest part of the liftoff deployment. On the other hand, China's FAST is a combination of tens of thousands of components, and when exposed to national wind and rain, maintenance problems will definitely occur, and the maintenance budget will increase every year, which is a common sense. Let's compare the working objectives of Webb and FAST. The two main scientific goals of China's FAST are to survey neutral hydrogen in the universe and to observe pulsars. The former is to study the large-scale physics of the universe, so to explore the origin and evolution of the universe, and the latter is to study the material structure and physical laws in extreme states. FAST will probe the universe at radio wavelengths, hunting for faint pulsars, mapping neutral hydrogen in distant galaxies, and searching for signs of extraterrestrial communications and intelligence. Webb's main scientific goal is to observe the early universe, particularly distant celestial bodies. The universe is expanding, and the farther galaxies we're emitting from, the more they have become infrared when they are now received by us. Using Webb to measure the infrared light and analyze the spectrum of the early universe, the photos and data obtained will definitely be a legend in human history. Looking forward to its first photos. It can be predicted that, like Hubble, Webb will be very productive. Let's see the scientific innovations of Webb and FAST. Both Webb and FAST are innovative compared to the previous similar versions of other telescopes. Webb's technology in foldable parts for mirrors and sunshield is the first in human history, has achieved a great success, and will open up new avenues for deploying vehicles in space. Webb's specially designed materials and equipment are also industry leaders, especially the light detectors and analyzers. Compared to the former number 1 radio telescope Arecibo, the most prominent innovation of FAST is that its reflecting surface is flexible. There is a metal cable mesh pocket built underneath the reflector surface. The mesh pocket can move the reflecting panels within a range of 300 meters, thus changing the shape of the reflector surface. More than 2,000 hydraulic actuators are used to achieve the precise positioning of the metal cable mesh pocket through expansion and contraction. As a result, the 4,450 reflecting panels of the telescope can form an instantaneous paraboloids from a spherical shape with a diameter of 300 meters in the direction of the radio source. This greatly improves the observation efficiency and allows the telescope to have a wider observation range, which can cover a zenith angle of 40 degrees. Shape transformation can imagine like this: a sphere with a diameter of 500 meters can be transformed into an infinite number of paraboloids with a diameter of 300 meters, then the focal points of these paraboloids will become a focal plane, located 140 meters to 170 meters above the reflecting surface, and the feeder receiver cabin can be pulled in coordination to these positions to collect the focus signals. FAST's AI-assisted feeder receiver cabin is another powerful innovation. It has a 200-meter motion area across the reflector surface and is driven by computer-controlled 6-wire cables. It can reach countless focal positions formed from the paraboloids on the reflector surface. These wire cables are specially designed with the characteristics of high elasticity, tensile resistance, and fatigue resistance. The steel cables designed for FAST were later used in other constructions, including the Hong Kong-Zhuhai-Macau Bridge. Another interesting aspect is the perforated reflector panels, with holes just smaller than the cosmic ray wavelength but can let go through rain, wind and light, a very smart design. Like Arecibo, FAST's feeder receiver cabin hangs high above the plate. The FAST's reflector surface pot is deeper and has a wider field of view than Arecibo's. It can cover a patch of sky within 40 degrees of the zenith, while Arecibo is limited to within 20 degrees of the zenith. FAST was built inside a natural depression in the limestone-dominated terrain, and it uses mountainous karst features surrounding the observatory to block out radio interference. Some building materials and technologies invented for FAST have also promoted the improvement of multi-field equipment manufacturing capabilities later. In the karst terrain of the Yunnan Guizhou Plateau, it is not easy to complete such a huge project with limited access to traffic and construction equipment at the early stage.